Hey guys, this video is going to be about rational functions and their graphs, and I want you to be able to identify properties of rational functions and also to be able to graph rational functions. So this section is going to have a good chunk of vocabulary that goes along with rational functions. You should be able, by the end of the section, be able to tell if something is continuous or discontinuous. Be able to define a rational function, be able to find and know what a horizontal and vertical asymptote are, be able to find points of discontinuity and whether those points are non-removable points or removable points. Okay, so if a function has a polynomial in its denominator, its graph has a gap at each zero of the polynomial. Okay, so the gap could be 1 point, meaning a hole in the graph, or it could be a location of a vertical asymptote. So when you're dealing with rational functions, it's written in the form, so a rational function right here is a function that you can write in this form, this p of x over q of x. And this is where p and q are polynomial functions. So here's what I know. When you got a fraction, the denominator can't equal 0. So the domain for this rational function is going to be all numbers, let me underline this, all real numbers, except, I call these red flags, where the denominator equals 0. So when the denominator equals 0, you're going to have either a vertical asymptote or a hole in your graph. Okay? So let's kind of figure out what continuous and discontinuous means. All right, so let me draw some graphs here. And these are on page 515 at the bottom. But I'll go ahead and give a graph here. So the equation is y equals x squared over x squared plus 1. Okay? Now, the domain for this is all real numbers except where the denominator is 0. So let's look at the x squared plus 1, this denominator right here. When will it equal 0? Well, let's see here. If I put in a positive number for x and square it, I got a positive, I add 1. Well, if I add 1, it's not going to equal 0. If I put in 0, I evaluate that, I get 1. If I put in a negative number and square it, I get a positive number, and then I'm adding 1. So this denominator will never be 0. So that indicates the domain for this function is negative infinity to infinity. Okay, so its graph. Let me give you a little graph of this. If you would put this function in your calculator, you're going to get a graph a little something like this. Okay, so notice the graph goes from negative infinity to positive infinity for your x values. If I can trace this, I'm going to go ahead and I'll trace it in blue. If I can trace this without lifting my pencil, it's continuous. Okay? It's going to be continuous if you have a domain that is negative infinity to infinity. Okay? All right, let's take a look at another equation. Let's say I have y equals the quantity x plus 3 times the quantity x plus 2 over the quantity x plus 2. Okay, here's what I see. I see that this x plus 2, if I can finish this parenthesis, this x plus 2 on top and bottom cancels. Okay, well, that leaves me with y equals x plus 3. Now that's all great except for it did have a denominator, and the denominator can't be 0. So when does it equal 0? At -2. That means I'm going to have a whole at -2. So if I would graph this function, I've got a y-intercept at 3 and down 2, left 1. Oh no, not left 1. Yes, left 1. Hold on. I think I messed that one up a little bit. So down 1, left 1. That's what I wanted. Down 1, left 1. Okay. Here's the function, x plus 3. Problem is, I have a whole at -2. So I need to draw this graph where, oh, I hit the eraser. Darn it. Might have to start over a little bit here. Actually, I am. I'm going to just start over. Let me erase. All right. So I have 1, 2, 3, 0, 3. I do know I have a whole at -2. If I put in -2 into that function, I get 1. So -2, 1 gives me a whole. Now I'll go ahead and do the slope, down 1, left 1. So notice my graph of this function, y equals x plus 3 times x plus 2 all over x plus 2. It ends up being a line. It has a hole in it. Well, if it's got a hole in it and I try and graph it, notice I have to pick up my pencil, right? If I have to pick up my pencil, that is called discontinuous. It has a point of discontinuity, okay? Now, this point of discontinuity is removable. It is removable discontinuity. Let me write that down, removable. Removable because I've plucked off one point off the graph, just 1 point. That is a removable point. I have removed 1 point off that graph. Okay? Now let's take a look at this graph, or this equation. X plus 4 over x minus 2. Okay, so looking at this, it looks like I have a possibility where the denominator is going to be 0, and it's going to be at 2. But notice there's not an x minus 2 on top and bottom. Okay? This is going to indicate a vertical asymptote. Okay? So if you can cross out something on top and bottom, you're going to have a hole. If you cannot, then the denominator, whatever makes that 0, will be a vertical asymptote. So I have a vertical asymptote at x equals 2. Okay, so I'm going to go ahead and show you what this graph looks like. I've got a vertical asymptote at x equals 2. Okay? And your graph is going to have branches. It'll look a little something like that. Maybe not exact, but that shape. Okay? And this is going to be discontinuous. Why? Well, because if I trace it, then I have to lift to trace the other branch. That is discontinuous. This is non-removable discontinuity. Because there's an infinite amount of points that I would have to remove on that vertical asymptote. So those are non-removable. Vertical asymptotes are going to be non-removable. holes are going to be removable. Okay? Another point of discontinuity, I don't know if you noticed it on this last example here, is a horizontal asymptote. This horizontal asymptote's at y equals 1 when you graph that. That is also a point of discontinuity. Okay. All right. So going back to these graphs, it says above, write the corresponding equations under each graph, which I did. Can you describe what is causing the type of discontinuity? Okay, so a point of discontinuity. Well, a point of discontinuity is where you have something in the numerator and the denominator. A point of discontinuity is when you have a hole. Okay? So in that case, our hole was at x equals negative 2. Okay? It has a hole at x equals negative 2 because x can't be negative 2. That is our point of discontinuity. The vertical asymptote is, I'll just put VA there, x equals 2. Notice that's in the denominator. Okay? It'll always be continuous when you have a domain of all real numbers, meaning negative infinity to infinity. Okay? Now let's talk a little bit about how I can look at these graphs or these equations and know if I have a discontinuity for a horizontal asymptote. Okay? All right, so if the function has a domain that includes all real numbers, then it's going to be continuous. And if the function can't be defined, meaning you can't factor it and simplify, you're going to have a vertical asymptote at whatever makes that denominator 0. So I would say, well, x minus 3 equals 0. So x equals 3 is going to be your vertical asymptote. Okay, so notice this last one. If you can redefine the function, in other words, if you can factor the top and bottom and remove the discontinuity, that means you're going to have a hole in your graph. Okay, so notice that x squared minus 3x minus 4 factors to x minus 4 times the quantity x plus 1. Well, the x minus 4 and the x minus 4 cancel. That leaves me, we redefine the function as y equals x plus 1. So when we redefine the function, that means I'm going to have a hole at that point of discontinuity that I removed. So x minus 4 equals 0. Well, that means x equals 4. Okay, so let's take a look here. Let's do some practice problems. What are the domain and the points of discontinuity for these rational functions? Remember, a rational function is just where you got a fraction. You have a polynomial on the top, you have a polynomial on the bottom. Okay, so taking a look at this first problem, y equals 1 over x squared minus 16. First thing you're going to do is factor. 1 over, that is the difference of squares, x minus 4, x plus 4. Okay, so now I'm going to look. Can I cross anything out? No. That means there's no holes. Will the denominator ever be 0? Yes, because this gives me an x equals 4, and that gives me an x equals negative 4. Okay, those are vertical asymptotes. They are non-removable points of discontinuity. Okay, so if they're points of discontinuity, that means my domain can be everything but negative 4 and 4. Okay? In other words, in interval notation, negative infinity to negative 4, union, negative 4 to 4, union 4 to infinity. Okay? So let's take a look at number 2. So we've got to see if we can factor. We can factor the top. That's the difference of squares, x minus 1 over x plus 1. Denominator does not factor. So looking at if there's a hole, is there something on the top and the bottom? No. So no hole. Will this denominator ever equal 0? Well, x squared plus 3 will never equal 0. So that indicates the domain is all real numbers, negative infinity to infinity. And if that is the domain, it is a continuous function. Okay, meaning there are no points of discontinuity. There's no holes, there's no vertical asymptotes, there's no horizontal asymptotes that interrupt the graph. Okay, so number 3, well, let's factor. We got x plus 1 on the top, and on the bottom, I've got x plus 2 times the quantity x plus 1. Well, here's what I notice. That x plus 1 is going to cancel. So that tells me that I have a hole. And I have a hole at x equals negative 1, because that's what would make that 0. Okay? That is removable, because I've only removed 1 point. That is a removable point of discontinuity. So the whole of x equals negative 1, removable point. But notice, when I simplify this, this becomes 1 over x plus 2. There's still something in the denominator. That something in the denominator is going to be a vertical asymptote. Vertical asymptotes at x equals negative 2. That is non-removable. That is a non-removable point of discontinuity. Okay, so with that, then that indicates that the domain is going to be everything but negative 2 and negative 1. So negative infinity to negative 2, union, negative 2 to negative 1, union, negative 1 to infinity. Okay. So hopefully you have a better idea of how to tell when you have points of discontinuity and whether those are going to be removable, non-removable, and how you find them. Let's take a look at horizontal asymptotes. Okay, so here's some rules for horizontal asymptotes. So if the degree of the numerator is equal to the degree of the denominator, okay, so notice this degree right there is 2, this degree right here is 2. Okay, the degree is going to be that highest exponent. Okay, when the degrees are the same, then that indicates that you are going to divide their coefficients. So notice you'll have a horizontal asymptote, a horizontal line at y equals 4/7. All right, so let's take a look at the second option. The degree of the top, well, if it's not written, let's see, in x, that would be a degree of 1. So if it has a degree of 1 and the bottom has a degree of 2, when the degree of the top is smaller than the degree of the bottom, you have an automatic horizontal asymptote at y equals 0. Automatic. When the degree of the top is smaller than the degree of the bottom. Automatic horizontal asymptote at y equals 0, which is on your x-axis. Okay? Now, if the degree of the top is bigger than the degree of the bottom. So notice I put that the degree of the bottom is 1. When the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote. So for that, when you write horizontal asymptote, you would want to write none to indicate that you know there is not one. Okay. All right, so let's take a look at some examples here. We'll put some things together. So what are the vertical asymptotes of the graph? All right, well, let's see. Vertical asymptotes. Well, let me get a color here. Nothing cancels for number 1. That means I'm looking at the denominator. So x equals 1, x equals negative 3. Those are your vertical asymptotes. For number 2, let's see. The x minus 2 cancels. So a vertical asymptote only happens at x equals negative 3. You technically have a hole at x equals 2. Okay. Looking at number 3, let's see the top factors into x minus 1, x plus 1, denominator into x plus 1. X plus 1 cancels. Now notice there's nothing left in the denominator. So there is no vertical asymptote, but you do have a whole at x equals negative 1. Let me go ahead and for number 2 write that whole, x equals 2, just to be complete. For number 4, let's see. Nothing factors, denominator will never be 0. There is no vertical asymptote because this is a continuous function. Okay. Now let's look at horizontal asymptotes. Okay, we're going to take a look here. The degree of the top, 1. Degree of the bottom, 1. Let me put that in there. That means we're going to divide negative 2 by 1. So y equals negative 2 is your horizontal asymptote. This is when the degree of the top equals the degree of the bottom. All right, let's take a look here. The degree of the top, well, it's 1. The degree of the bottom is 2. Let's see, the degree of the numerator is greater than the degree of the denominator. Well, that's an automatic horizontal asymptote. Let me get my pen. At y equals 0. Okay. Looking at number 7, degree of the top, 2. Degree of the bottom, 1. When the degree of the top, the numerator, is greater than the degree of the bottom, the denominator, there is no horizontal asymptote. Okay. All right. So lots of information, lots of vocabulary. Hopefully you know what it means to be continuous or discontinuous, what a rational function is, how to find horizontal and vertical asymptotes, and how to find points of discontinuity, and knowing whether they are removable or non-removable. Okay. Got a few more examples here for you. What are the domain and the points of discontinuity? All right, so for this guy, what you want to do is factor first. So if you have y equals x squared minus 1, that factors into x minus 1, x plus 1. The denominator, well, let's see, x squared minus 6x plus 5, that factors into x minus 5, x minus 1. Okay, here's what I know. X minus 1 cancels, okay? So what does that tell me? That tells me that I have a whole at x equals 1. That is removable. That is a removable point of discontinuity. Okay? So when I simplify this, I get x plus 1 over x minus 5. All right, well, that tells me right here that's going to be a vertical asymptote. I have a vertical asymptote at x equals 5 because that's what makes the denominator 0. So how do I find my domain? Well, your domain is always going to be all real numbers, but your wholes and your vertical asymptotes. Well, all real numbers, but 1 and 5. So that means in interval notation, that is negative infinity to 1, union 1 to 5, union 5 to infinity. That would be your domain and how to find your points of discontinuity. Next example. What are the vertical asymptotes and horizontal asymptotes? Well, first thing you've got to do is factor. You have x plus 3 on the top. That's its own linear factor. I like to sometimes just put that in parentheses. Denominator is going to factor, and it's going to factor into x plus 4 and x plus 3. Notice the x plus 3 cancels. Well, what does that tell me? That tells me I have a whole at x equals negative 3. That is a point of discontinuity. It is a removable point of discontinuity. However, it asks for vertical asymptotes. When I simplify this, I get 1 over x plus 4. I look at this denominator for vertical asymptote. So a vertical asymptote is when the denominator is 0. X equals negative 4 is my vertical asymptote. Now, for a horizontal asymptote, this is where you want to look at the degree of the top, and I'm going to start from the original. The degree of the top, well, it's 1. The degree of the bottom is 2. When the degree of the numerator is greater than the degree of the denominator, that means you have an automatic horizontal asymptote at y equals 0. Okay. All right. I do believe this might be our last example. I'm double checking, yes. All right, so last example here. Sketch the graph of the rational function. So I have x plus 2 over x minus 1. So this is kind of where we're just going to put it all together. Okay, so here's what I know. Domain and range. I tend to do those a little later. I will look for my points of discontinuity and my asymptotes first. Okay, so vertical asymptote. Well, maybe let's start with holes. The top is its own group. The bottom is its own group. Nothing cancels. That means there are no holes. So there are no points of discontinuity. I'll put none here. Okay. Now, non-removable points of discontinuity. That goes with your vertical asymptotes. Vertical asymptotes are found looking at the denominator of your rational function. So x equals 1. X equals 1. That is non-removable point. It's a vertical asymptote. Okay. Taking a look at horizontal asymptote, degree of the top, 1. Degree of the bottom, 1. When the degree of the top is the same as the bottom, then I'm going to divide their coefficients. So 1 divided by 1, y equals 1 is a horizontal asymptote. Okay, let's go ahead and graph a few things here. Vertical asymptote, x equals 1. Vertical asymptote, x equals 1. Okay, we have a horizontal asymptote, y equals 1. All right, let's get some intercepts here. The interesting thing is that the intercept, the x-intercepts, are the zeros of the numerator. So that's going to be x equals negative 2. In other words, negative 2, 0 is an x-intercept. Okay. Y-intercept, we'll plug in y is 0. When I plug in 0, then I'm going to have on the top y equals, not y equals 0, x equals 0. Gracious. X equals 0. Okay, plugging in x equals 0, I have 0 plus 2 over 0 minus 1. That's 2 over negative 1 equals negative 2. That gives me the point 0, negative 2. Okay. Notice when you have to take into account their signs, the constants for each will give us our y-intercept. All right, so let's go ahead and graph it. There's one branch. Okay. I can do the other branch, all right? So one thing that you could do is if I wanted to, I could plug in 2 and I get 4. And if I plug in 4, I get 2. And there's my other branch. So I'm just plugging in points that would be in that branch for that x values. Okay. All right, so let's take a look at what we have. Your domain is going to be everything but vertical asymptotes and holes. Well, what do we have? Vertical asymptote is 1, everything but 1. Negative infinity to 1, union 1 to infinity. The range is going to be everything but the horizontal asymptote. So the horizontal asymptote is at y equals 1, so everything but 1. Negative infinity to 1, union 1 to infinity. All right? So lots of information, but you've got to be able to first find those points of discontinuity, find vertical asymptotes, horizontal asymptotes. You guys have worked a long time with finding x-intercepts and y-intercepts, but I did want to show you how you can find that x-intercept and y-intercept just from the equation of your rational function. Using all that information, you can find your domain and range of your function as well as graph it. Hope this helps you out a little bit.